63 light-years away, inside one of the most photographed, most closely studied star systems in the history of astronomy, there was a planet nobody had ever noticed. Not because it was too far away, not because it was too faint. It was hiding in plain sight, buried inside a blinding disk of dust so bright that no camera, however powerful, could ever pick it out from the glare surrounding it. Astronomers had studied this exact system for decades, found 2 other giant planets in it, and never once suspected a third was sitting there the entire time. Then, in July 2026, a team wasn't even looking for it, and they found it anyway, not by seeing it, but by reading the chemistry of the air wrapped around it. Tonight, we're looking at how the James Webb Space Telescope found a planet no telescope has ever managed to photograph, why the method used to confirm it might change how we search for hidden worlds everywhere in the galaxy, and why this discovery happened almost entirely by accident. To understand why this find is such a big deal, you first have to understand just how thoroughly astronomers thought they already knew this particular star system. Beta Pictoris sits 63 light-years from Earth, a young star only around 23 million years old, still surrounded by a vast, glowing disk of leftover dust and debris, the raw material planets are built from. It's one of the most iconic planetary systems in modern astronomy, partly because it gave scientists one of their first ever direct images of an exoplanet. Beta Pictoris b was confirmed back in 2008, followed by a second giant planet, Beta Pictoris c, in 2019. Finding even one directly imaged planet is difficult. Finding 2 in the same system made Beta Pictoris one of the best-studied planetary neighborhoods outside our own solar system, a place astronomers return to again and again with better and better instruments, assuming there was nothing left to find that hadn't already been cataloged. Consider just how much attention this one system has received over the years. Beta Pictoris has been observed by ground-based observatories, by Hubble, and now repeatedly by Webb across nearly 2 decades of dedicated study. Entire careers have been built analyzing its debris disk, tracking the orbits of its 2 known giant planets, and using it as a kind of natural laboratory for understanding how planetary systems form in their earliest, dustiest stages. If there was ever a system where astronomers felt confident they'd found everything worth finding, it was this one. That's precisely what makes the existence of a completely unnoticed third planet so remarkable. It wasn't sitting in some rarely observed corner of the sky. It was hiding inside the single most scrutinized planetary system available to modern astronomy. That assumption turned out to be wrong, and the way it fell apart is almost stranger than the discovery itself. In July 2026, a research team led by Aidan Gibbs and Jean-Baptiste Ruffio at the University of California, San Diego, was using Webb's near-infrared spectrograph, specifically its integral field unit, to study the atmosphere of the already known planet, Beta Pictoris b. They weren't hunting for anything new. As Ruffio later put it plainly, the team wasn't looking for a new planet at all. They were simply trying to understand one that had already been confirmed nearly 2 decades earlier. But the instrument they were using does something unusual. Instead of just capturing a single image, it records a full spectrum, essentially a chemical barcode, from every individual point across the observed field all at once. Buried in that flood of spectral data was a pattern that didn't belong to dust. Ordinary debris in a disk like this one produces a smooth, gradually sloping spectrum, nothing sharp or distinctive. What the team found instead was a series of repeated peaks and dips, a jagged, structured signature completely unlike the surrounding dust. When they identified what was producing it, the answer was carbon monoxide, a gas commonly found in the atmospheres of giant planets. It was showing up at a location in the system where, according to every existing catalog, nothing was supposed to be. This is the part of the discovery that makes it genuinely different from almost every exoplanet found before it. Nearly every directly imaged planet in history, including Beta Pictoris b and c themselves, was found the same way. Astronomers spotted a faint point of light near a star and confirmed it was a planet through follow-up observations. This new object, eventually named Beta Pictoris d, was never spotted as a point of light at all. It was identified purely from its chemistry, the carbon monoxide absorption, lines threaded through Webb's spectroscopic data, long before any camera managed to isolate it as a distinct object separate from the glowing debris disk surrounding it. Researchers were also able to measure the Doppler shift of those same spectral lines, the subtle stretching and compressing of light caused by an object's motion toward or away from us, which let them calculate the object's radial velocity and confirm it was genuinely orbiting the star, not simply an unrelated object drifting past in the same direction. The team calculated that the odds of this actually being a chance alignment with some unrelated background object, rather than a real planet bound to Beta Pictoris, were less than 1 in 10 million. It's worth sitting with how counterintuitive this discovery method actually is. Normally, confirming a planet means catching its light directly, however faint, and separating that single point from everything around it. Here, Researchers never isolated a clean point of light at all. They found a pattern of absorption dips scattered across a busy spectral field, recognized that pattern as chemically inconsistent with ordinary dust, and used the object's own motion through space to prove it was gravitationally bound to its star rather than some coincidental alignment. In a very real sense, the planet announced itself not through its light but through its breath, the specific gases filling its atmosphere, detectable even while the object itself remained completely unresolved as a distinct shape in any image. Independent confirmation came quickly. A separate team, led by Ben Sutcliffe at the University of Edinburgh and Marcus Bonce at the European Southern Observatory, combined data from the European Southerns Observatory's very large telescope with additional imaging from Webb's own near-infrared camera, and independently verified that Beta Pictoris d was real. Later, follow-up observations using Webb's mid-infrared instrument added even more detail to the picture, detecting not just carbon monoxide, but also methane and water vapor in the planet's atmosphere. A genuinely detailed chemical profile for a world that, only months earlier, nobody even knew existed. So what exactly is Beta Pictoris d? Based on the data gathered so far, it's a giant planet estimated at a minimum of roughly twice the mass of Jupiter, making it the smallest of the 3 known planets in the system despite its size still, dwarfing anything in our own solar system. It holds the widest orbit of the 3 confirmed Beta Pictoris planets, circling its star at a distance of roughly 30 astronomical units, comparable to where Neptune sits in relation to our own Sun, though still tucked just inside the inner edge of the system's bright debris disk, exactly the region where its light would have been hardest to separate from the surrounding dust using conventional imaging. That positioning explains precisely why it managed to stay hidden for so long, despite Beta Pictoris being one of the most intensely observed planetary systems in the sky. It wasn't distant. It wasn't faint in any absolute sense. It was simply standing directly in front of one of the brightest, busiest backdrops in the entire system, camouflaged by exactly the kind of material planets like it are born from. There are real limits to what this detection method can currently tell us. Unlike a direct image, which lets astronomers estimate a planet's physical size and brightness fairly directly, this spectroscopic detection technique confirms a planet's existence, its chemical composition, its temperature, and its orbital motion. But it doesn't, on its own, pin down the object's physical radius. Those measurements will require different follow-up observational techniques, and researchers are already planning them. What the discovery does prove, immediately and unambiguously, is that Beta Pictoris d is real, chemically distinct from its surroundings and gravitationally bound to its star. The bigger implication here reaches far beyond this one particular planet. For decades, the search for new worlds around other stars has depended heavily on either watching for the tiny dimming caused by a planet passing in front of its star, or, in rarer cases like Beta, Pictoris b and c, directly photographing a faint point of light separated from its host star's glare. Both methods run into the same fundamental problem in systems like this one: bright, busy, dust-filled environments, where a planet's light gets lost entirely in the surrounding noise, no matter how sensitive your camera is. Beta Pictoris d proves there's a third way. If a planet's atmosphere produces a strong enough, distinctive enough chemical signature, astronomers may be able to find it purely by reading that chemistry, even in cases where direct imaging would never be able to isolate it from its surroundings at all. That has real implications for how many hidden worlds might already be sitting in systems we consider thoroughly explored. Beta Pictoris was about as well-studied a planetary system as exists anywhere in modern astronomy, examined repeatedly for nearly 2 decades by some of the most capable instruments ever built, and it still had an entire giant planet hiding inside it that nobody suspected was there. If a world this substantial could stay concealed in one of astronomy's most closely watched systems, it raises an obvious question about how many uncatalogued and other dusty, actively forming systems astronomers have already examined and assumed they'd fully mapped. That question matters enormously for the broader search for exoplanets, and for eventually finding potentially habitable ones. Many of the most scientifically interesting stages of planet formation happen precisely in these young, dusty, actively forming systems, exactly the environments where direct imaging struggles most. If spectroscopic detection can reliably find planets hidden inside that kind of glare, astronomers gain an entirely new tool for studying planetary systems at the exact stage of their development when the most dramatic changes are still happening, rather than being limited to older, cleaner systems where the dust has already settled and planets are easier to photograph directly. Researchers are already discussing applying the same technique to other young, dust-rich systems that have been imaged repeatedly over the years. Systems that, like Beta Pictoris, may be hiding worlds nobody has thought to look for using anything other than a camera. For now, Beta Pictoris officially becomes only the second known planetary system with at least 3 confirmed, directly detected worlds, a genuinely rare distinction in exoplanet science. And it got there not through a bigger camera or a longer exposure, but through astronomers paying close enough attention to a spectrum they weren't even specifically looking for, noticing that a jagged chemical signature didn't belong to dust, and following that thread all the way to a previously invisible world. It's a reminder that some of the most significant discoveries in modern astronomy don't come from pointing an instrument at something new. They come from looking more carefully at something everyone already assumed had been fully understood. If you want to be here the next time a hidden planet turns up in a system we thought we'd already fully mapped, subscribe and turn on notifications, because if Beta Pictoris d could hide in plain sight for nearly 2 decades of intense observation, there's no telling how many other worlds are still waiting quietly in the data we already have. Chemical signatures sitting unnoticed in archives astronomers assumed had already given up everything they had to offer.